last lecture on chapter 5, that is on open systems. Let me give you a brief overview of what we have covered so far. We started with this chapter with the understanding that we'll have two sorts of equations that we'll develop for the open systems. One is the uh, mass balance equation, and the other is the energy balance equation. So we developed those equations for an open system, and we looked into the fact that open systems essentially they operate under steady state conditions for most of the time. So we modified the equations, or we looked into the modification of the equations for steady state operations. That is, the operations that do not have change in property with regards to time in the control volume, and as well as the properties which are entering and leaving the control volume. Once we had those equations, we applied those equations on a specific components, engineering components. The first set of components that we looked into were nozzles and diffusers, and we applied the energy balance and mass balance equations on nozzles and diffusers. We looked into some of the examples for the two components. Then we had the second set of components, which included the compressors and the turbines. We looked into the operation of turbines and compressors and the fact that turbines normally involve work out of the system, and compressors normally involve work into the system. And we also mentioned that compressors, fans, and pumps then essentially operate, so they operate under the same principle. The third category of component that we looked into was mixers. And in mixers, we said that there is a physical mixing of fluid taking place within the mixer, and we applied the energy balance equation onto mixer, and we looked into one of the examples for mixers. The component that we are going to we are going to look today into is essentially the heat exchangers. Heat exchangers, they are essentially working under the same philosophy that there is a heat transfer that is associated, but the only difference between heat exchangers and the mixers is that in heat exchangers, there is no physical mixing of the fluids. Essentially, there are two moving fluid streams that are involved, and they exchange heat with each other without physical mixing. So there is no physical mixing that is being involved in the process. They are widely used in various industries, and they come in various designs. So one of the designs that we look into is a design where you can have the heat transfer associated with the heat transfer associated with the heat exchanger. It depends upon how the control volume is selected in a heat exchanger. The heat transfer could essentially be zero, or it could be non-zero. It again depends upon how you select the control volume. For instance, I have the same heat exchanger. Now, what is happening in this heat exchanger is that there is a fluid which is through pipe and leaving from this side. So there's a fluid going to the pipe, and within this chamber there is another fluid which is entering into the chamber from this end, which is at the upper side of the chamber, and the fluid enters, flows outside the pipe, and leaves through this chamber from the exit, which is at the bottom. So fluid is flowing out, fluid B is flowing outside the spray pipe, and it is moving out of the box. And for this system, where you have a fluid going through the pipe into the inside of the pipe, and there is another fluid which is going through the outside of the pipe, you have selected the whole box as the control volume. Now, essentially, there is a heat transfer if this fluid B is hot and fluid A is relatively at a colder temperature. There would be heat transfer from fluid B to fluid A through this pipe. But essentially, if you have selected this whole boundary as your control volume, I am showing you in 2D. If you have selected this whole boundary as your control volume, essentially there is no heat transfer across this boundary. There is no heat that is flowing out of this boundary, and there is no heat transfer that is flowing to the inside of this boundary. this heat transfer, which is from fluid B to fluid A within the control volume. This, since it is not crossing the control volume boundary, you would consider this as a case where your control volume would have zero heat transfer. The same configuration where you have selected the periphery or the boundary of the pipe in which fluid A is flowing, again showing in a 2D view. If that is your control volume, if this is your control volume, essentially there is a heat transfer taking place from the outside through the pipe to the fluid flowing inside the gray pipe. So that would, in such a case, there would not be the heat transfer would not be. Is this point is, is this point clear to you? That depending upon the control volume, you may or may not have any heat transfer involved in the process. Abu, is it clear to you? Can you hear me?
सर आपकी आवाज़ बहुत ज़्यादा डिस्टॉर्ट हो रही है।
तो बेटा ही पूछने पे आप बताएंगे मुझे।
नो सर, ये अभी जब आपने पूछना शुरू किया तो उस वक्त बहुत ज़्यादा हो गई।
सर अब ठीक आ रही है।
But before that, all right. But before that, the concept of heat transfer, is it clear to you? It could be
Yes,
zero,
sir.
it could not be zero, depending on the control volume. All right. If it is clear, then let's move ahead. So
Yes,
in a case, all right. So just degree centigrade, which is entering from inlet 1 and leaving from the inlet 2 at 25 degrees centigrade. So the water is gaining heat. Similarly, there is another fluid R310 refrigerant with us, and this is the pipe. So within this great pipe, the fluid which is flowing is refrigerant R134 at 35 degrees centigrade. That means it is losing heat to the water and cooling itself down as it flows from the inlet 3 to inlet 4. Now, if this is taking place at the mass flow rate at the inlet 1 is essentially the same at inlet 2. That means whatever amount of mass flow rate of water is entering into the system, it is the same as it is leaving the system. So you can call it as mass flow rate of the water. Similarly, the mass flow rate at inlet 3, whatever amount of refrigerant is entering into the system, is essentially leaving the system at the exit through the mass flow rate 4, which means that mass flow rate at the inlet 3 is equal to the mass flow rate at the exit 4, which is the mass flow rate of the refrigerant. Whatever amount, at whatever rate the refrigerant is entering into the system, it is leaving the system at the same rate. This is the mass balance equation for the heat exchanger. So the mass balance equation, again, for an adiabatic heat exchanger or otherwise, would be that the rate of mass entering through inlet 1 would essentially be equal to the rate of mass leaving the system from exit 2, which is essentially equal to the mass flow rate of water, and mass flow rate of refrigerant at the inlet 3 is essentially equal to the mass flow rate at the exit 4 for the refrigerant. Now, mass balance. If you talk adiabatic heat exchanger would essentially have heat transfer as the zero, or heat transfer rate would be zero for this control volume. If you take the whole system as the control volume, so there would be zero heat transfer. Work done, since there is no electrical or shaft work involved, work done would essentially be zero. Since the fluid is entering roughly at the same energy and elevation, the kinetic energy and potential energy are also assumed to be zero. So the only energy associated with the system is the energy of the mass that is coming in leaving the system, which is associated with the enthalpies. So you would have essentially the enthalpies associated with the mass flow rate coming into the system as m dot h1. This is coming from water, and m dot 3h3, which is coming from refrigerant. This is the energy coming into the system, and the energy leaving the system is m dot 2h2, which is the enthalpy associated with the mass flow rate which is leaving the system, and the enthalpy m dot 4, which is the enthalpy associated or the energy associated with mass which is leaving the system in terms of. So we have an example which says that a refrigerant R134A, again, when you have R134A, you would go to the table R134A or utilize the tables R134A. It is to be cooled by water in a condenser. When you have water, you will go to steam tables. The refrigerant enters the condenser with a mass flow rate of 6 kgs per minute. So you have the mass flow rate of refrigerant known to you. And the inlet conditions are 1 megapascal 70 degrees centigrade and leaves at 35 degrees centigrade. The cooling water, again, the entering condition is 100 kilopascal 15 degrees centigrade and it leaves at 25 degrees. Neglecting any pressure drops. That means the refrigerant is leaving at 1 megapascal and the water is leaving at 300 kilopascal. Determine the mass flow rate of cooling water required from the refrigerant. Let's first look at the first part. This is the schematic. We have already seen the schematic, the energy is associated, and the mass balance equation. The mass balance equation says M in equals to M out. Since each fluid is flowing independently and there is no physical mixing, you would have the mass flow rate at 1 is equals to at 2, which is the mass flow rate of water, and at 3 equals to 4. The inlet and exit are same, and that is the mass flow rate of the refrigerant. Now, at this mass flow rate, you have the energy balance equation, which says energy which is coming from water and refrigerant entering the system is essentially equal to the water and refrigerant leaving the system. So if I combine the water terms on the left hand side, I would essentially have the m dot 1 h1 plus minus m dot 2 h2. So I'll take the water term on that side and I'll take the refrigerant term on the right hand side. So I'll have m dot 4h4 minus m dot 3h3. Now the refrigerant terms are on the right hand side and the water terms are on the left hand side. Since I know from this equation, mass balance equation, that m dot 1 and m dot 2 they are same, I can express the equation in this form: m dot water, which is common, is essentially h1 minus h2, and this is essentially equal to m dot refrigerant, and m dot 3 and 4 are is same, h4 minus h3. This would be my equation, modified equation for the energy transfer. Now, with this equation in mind, I know the value of m dot r. This refrigerant mass flow rate is known to me. I have to find out the m dot w. If I could somehow find out h1, h2, h4, and h3, I can essentially solve the equation for mass flow rate of the water. Do you have any idea or do you have any suggestions how we can find out the mass flow rate or the enthalpies of the corresponding states?
Using tables, sir.
Yes, using the respective tables. For water, you would use steam tables, and for a refrigerant R134A, you would use R134A tables. Now, let's first consider water, the enthalpies of water H1 and H2. It says that at 300 kilopascal, the pressure for both the conditions, the saturation temperature is 133.52, and both the temperatures for water, 15 degrees centigrade at the inlet and 25 degrees centigrade at the outlet, they are less than the saturation temperature. This means that you will have at both the conditions water as compressed liquid, and the approximation for compressed liquid is that of saturated liquid at the given temperature. So the enthalpy for water H1 is essentially HF at 15 degrees centigrade, and the enthalpy at exit for water is essentially HF at 25 degrees centigrade. Once you go to table E4, which is against the table, against the temperatures, you will find H1 to be HF at 15 degrees centigrade and H2 to be HF at 25 degrees centigrade, both the same. Refrigerant R134A, you will go for the first condition. The refrigerant enters the condenser as superheat vapors and leaves as compressed liquid at 35 degrees constant, 1 megapascal and 70 degrees centigrade. So for this condition, the refrigerant, if you go and find the properties in the table for the refrigerant, you'll see that these conditions region for the refrigerant R134. So you'll use A to D, which is a superheated table for refrigerant R134, and this would give you the H3 value to be 303.8. Similarly, if you go and have a look at the value, the refrigerant at 1 megapascal and 35 degrees centigrade, this is compressed liquid region. So you can approximate this value with the saturated approximation, which is HF at 35 degrees centigrade from table A11. So this comes out. Once you plug in the values of the enthalpies, the corresponding water enthalpies and the refrigerant enthalpies, and you know that the mass flow rate for the refrigerant is given to be 6 kgs per minute. So this is given to you. You just need to plug in the value and find out the mass flow rate for water. Now, the second part is where you have to determine the heat transfer from the refrigerant to the water. In such a case, you have to consider this sort of control volume where there is a heat transfer between the two fluids taking place. So this case, the first case you have selected a control volume, there is no heat transfer involved. But since the question asks about the heat transfer between the two fluids, you'll have to change your control volume so that your heat transfer is not equal to zero now. If you take this example, steam entering at lower temperature and leaving at higher temperature, and water and refrigerant entering at higher temperature and leaving at lower temperature, means there is a heat transfer from the refrigerant to the water, which is represented by gray color. So there is a heat transfer that is being involved. In such a case, you can take the control volume as the portion that represents water. So this could be your control volume. If you see this control volume, there is a heat transfer which is moving into the system. There is energy which is entering into the system in terms of mass flow rate. So there is m dot h1 which is entering into the system, and heat which is entering into the system. Q dot is entering into the system, and the energy leaving is essentially the energy of the fluid which is leaving the system, which is m dot 2 h2. So you'll have a modified equation. Would be a modified equation, and this is an equation where you have Q dot W into the system. This is the energy being supplied to the water, which is essentially the same thing as Q dot R out of the system, the energy heat lost by the refrigerant. So if you look at the energy balance equation, the energy balance equation is the heat being supplied to water and the energy of the water which is entering the system associated with its enthalpy and mass flow rate, and the energy which is leaving the system is essentially the enthalpy associated with mass flow rate of the water which is leaving the system. Now, if you simplify this equation, H2, H1, they both are known from the first part. Mass flow rate you have calculated in the last part. You just have to plug in the values of the enthalpies and the mass flow rate to calculate the Q dot W in, which is the energy or heat gained by water, or it is the same thing as the heat lost by the refrigerant. The last component that we'll be looking into is essentially the pipe and duct flow. So they are essential components. They are used to connect different components. They are separately used for different applications. The the flow through a pipe or a duct, it usually satisfies the steady flow conditions. And these pipes and ducts, they are very frequently involved in air conditioning and refrigeration applications. So pipe or duct flow, it may involve more than one form of work at the same time. So there is shaft work, there is electrical work, both of the work could be involved. Heat losses from a hot fluid flowing through an uninsulated pipe or duct to a cooler environment may be significant, so you cannot. There is work associated with pipes and ducts. There is heat transfer associated with the hot fluid, which is surrounded by an atmosphere which is at lower temperature, and there is no insulation. So in such a case, there could also be heat transfer involved. This if you have a pipe and a duct where there is electrical work being supplied to the system, so there is work into the system, there is heat lost from the fluid which is flowing through the system to the surroundings. There is fluid which is entering into the system and leaving the system at different conditions. In such a case, the energy balance equation would be the electrical work into the system plus the energy due to the mass flow rate which is coming into the system is essentially equal to the heat lost by the system and the energy carried by the fluid from the system as it leaves the system. In case where you have fluid as the ideal gas, you can convert dH into CpdT, which we have done over here. So this is associated with the upcoming example that we are about to look into. The upcoming example that we are about to look into is an example where you have an electric heating system. So you have an electric heating system which is used in many houses and consists of simple duct with a resistance heater. Air is heated as it flows over the resistance wire. Air is an essential term over here. Consider a 15 kilowatt electric heating system. That means this 15 kilowatt is essentially the W dot into the system. Air enters the heating section at 100 kilopascal and 17 degrees centigrade. This is the inlet conditions, and the volume flow rate is 150 meter cube per minute. If the heat loss from the air to the duct is surrounding is 200 watt, this is Q dot out or loss per system. Determine the exit temperature, which is T2. So if you look at the schematic, you essentially have fluid moving into the system, enthalpy associated with it. Fluid leaving the system, so there is enthalpy associated with it. There is work into the system, which is work electrical in. There is heat loss, which is essentially equal to Q dot out and given the value. So if you apply the energy balance equation, you have two terms that contributes towards the energy coming into the system, these two, and two terms that are associated with the energy lost by the system. These are these two terms on the right hand side. Now, if you look at the equation, work electrical in, it is given to you. Q dot out, it is given to you. Uh, so if I take the exact terms which are given to me on the left hand side, I'll essentially have work electrical in Q dot out. So on the left hand side, mass flow rate multiplied by Cp T2 minus T1. It is essentially you have converted dH or H2 minus H1 into Cp dt. This is the conversion that you have used since you have air, which could be assumed as the ideal gas. Now, in this case, you have to find out the final temperature. Work electrical in is given, Q out is given, T1 is given, T2 you have to find out. How can I find out the mass flow rate? Any suggestions? Is there
Volume
any
flow rate given here, density फिर temperature से
density?
ideal gas equation से find करेंगे.
Very good, very good. So the mass flow rate, the relationship of mass flow rate is essentially equal to density multiplied by the volume flow rate, or volume flow rate divided by the specific volume. Volume flow rate, as you know, it is given to me. The specific volume, since we have assumed air to be an ideal gas, we can apply the ideal gas relationship, which is PV equals to RT, or specific volume is equals to RT over P. this would give me the specific volume. Plug it into the equation and you can find out the mass flow rate. Cp again is the value that you can extract from the table for air as the ideal gas at room temperature. Now, the ideal gas relationship, the specific volume will be. Now, if you apply this equation, V1 RT1 P1 T1 is given to you. R is 0.287 for air, again in kilopascal, so you'll have pressure in kilopascal. Temperature again you'll have in Kelvin. This would give you the specific volume. Now, if you have the specific volume, we'll just divide the volume flow rate. This is the volume flow rate given to you in the statement. You divide with the specific volume. This would give you the mass flow rate. Once you have the mass flow rate, you essentially can solve the equation. This is the work electrical in. This is the heat loss. Again, remember this was 200. Sorry, this value heat loss was 200 watts, and the whole equation is in kilojoules, so you'll have to divide by 1000. This is 0.2, then 15 kilojoules per second. 3 kgs per second is the mass flow rate you have found out. Cp value you have extracted for air at room temperature as an ideal gas on the table. Initial temperature is given to you, and T2 you can find out as 21.9 degrees centigrade. Now, this brings us to the end of the devices that we had to look into. The last portion of our discussion on chapter 5 is basically the energy analysis of unsteady flow processes. Now, when we say unsteady flow processes, we basically refers what we understand is that these are the processes in which the properties within the control volume they change with time. Such processes are unsteady flow or transient flow processes. We'll deal with a specific case of unsteady flow processes or transient flow processes, which is uniform flow processes. It says that most unsteady flow processes, they can be represented reasonably well by uniform flow process. In this process, what you say is that the properties at the inlet and exit, they essentially do not change with time. So at or exit is uniform and steady. The fluid properties do not change with time or position over the cross section of an inlet or exit. Even if they do, you take an average value for the time and position, and they are assumed as constant for the entire process. However, within the control volume, the properties may change with time. So this is the specific case of unsteady flow process. You have a gas and you have a valve connected to the control volume. Initially, the at time t equals to 0, the mass of my control volume is essentially 0. As I open t equals to 0, the valve is closed. As I open the valve, let's say for 3 hours, so t equals to 3 hours. After 3 hours, the mass within the control volume M2 would be changed, would have some value, let's say x, at 3 hours. So the mass at some other time, it has changed within the control volume. It is not 0 now. However, so this control volume is not under steady state conditions for the time from 0 to 3 hours. However, the mass flow rate or mass coming into the system through this mass flow rate through this valve, it remained constant for m dot I or mi. Sorry, inlet, since we don't have an exit, I would represent it by I as an inlet. This remained constant throughout the 3 hours. So we are assuming that this mass coming into the system, it is coming under steady state conditions. However, the properties within the control volume, they may change. Again, we could have another example where the volume and shape or size of the control volume it changes. Mass is coming into the system with time, and the boundary is moving ahead. So the control volume shape and amount of the mass in the control volume it is changing. But whatever is entering through the system, it is entering at a steady state rate. All right. In such a case, if you have to examine the system, you are basically, if you remember the equation, you have m in minus m out is equals to change in mass of the system. So what we're saying essentially is that the inside m in minus m out, this is not changing, only the change is taking place within the system. This is what we are referring to. So mass balance equation, you have essentially m in minus m out equals to change in mass of the system. Now, change in mass of the system is represented by two states, the final state and the initial state. The state at time t equals to 0 and tf when the process has completed. And you have m inlet minus m exit is essentially equal to change in the mass of the control volume. Similarly, the energy balance equation, it refers to the energy transfer due to heat, work, and mass. So you say that heat is coming in, work is being done on the system. M theta, this is referring to the inlet, and the mass flow rate at the inlet or mass at the inlet, it is constant and steady throughout the process. Similarly, Q out, W out, and M out, this is at the exit. Again, this is also constant. What is not constant is basically the mass at the initial state and the mass at the final state. This is the energy of the system. Energy of the system E1 is it's basically the energy of the system due to internal energy plus kinetic energy plus potential energy. So this E small e represents the energy content with regards to mass having these three energies. If you look at these theta and E, you already know them. If you plug these into this equation, you'll have Q minus W is essentially equal to the energy flowing out of the system as a result of enthalpy, the energy flowing into the system as a result of enthalpy, and the change in energy content of your system as a result of mass flowing in and out of the system. So again, a uniform flow process may involve electrical work, shaft work, and the boundary work associated with the system. And if you look at this equation, if I have closed the inlet and the outlet, so the inlet and outlet, they are closed, so there is no mass flowing into the system. In such a case, if there is no mass flowing into the system, this term would be 0, and essentially Q minus W is essentially equal to M2U2 minus M1U1, which is essentially the same thing as, since the mass is constant now, M2 would be equal to M1, and you will essentially have it is equal to delta U. So Q minus W equals to delta U is a special case for uniform flow process where you have inlets and exits closed. When you have inlets and exits closed, you will have Q minus equals to delta U, Q minus W equals to delta U as a specific case, which is this case for the closed system. So let us have a look at an example which says that a rigid insulated tank is initially evacuated. Evacuated means that M at state 1, M1 is essentially 0. It's connected through a valve to supply line that carries the steam at 1 megapascal and 300 degrees centigrade. So the steam is moving through the supply line at 1 megapascal, 300 degrees centigrade. Now the valve is opened. The steam is allowed to flow slowly into the tank until the pressure reaches to 1 megapascal, at which point the valve is closed. So at state 2, you only need the property of steam in terms of pressure. Determine the final temperature of the steam in the tank. So if you look at this is the conditions at the inlet. Since at the time t equals to 0, your is 0, m1 is 0. Your system is it doesn't have, we'll see about m2, and there is one inlet. However, there is no exit from the system. If you look at the mass balance equation, it says that m in minus m out is essentially equal to m2 minus m1, the mass at the final state and the mass at the initial state. There is no exit, so m out is essentially 0. There is no mass leaving the system. Initially, the mass of the system at time t equals to 0, m1 is equals to 0. So you have essentially mass inlet, m inlet is essentially equal to the mass at the final state. So whatever entered through the inlet was there in the system at the final state. This is what it is. And if you look at the energy balance equation, there is insulated tank. So insulated tank means Q dot or Q is 0. There is no work associated with it, shaft, boundary, or electrical work. So W dot is equal to 0. Again, kinetic and potential energies, they are almost negligible. So in such a case where you have Q 0, W outlet, so there is no mass flowing out of the system. This is 0. If you can, the mass at the initial state T goes to 0, M1 is 0, so this term is 0. Essentially, you have a single inlet, so MI HI is essentially equal to M2 U2. And if you look at the mass balance equation, Mi and M2, they are same. So Mi and M2 would cancel out. You essentially have enthalpy that entered through the system, which is Hi, is essentially equal to the internal energy of the system at final condition. So whatever amount of energy that entered in terms of enthalpy through the inlet is essentially equal to the energy stored in the system in terms of internal energy. I hope this is clear to you. So with this assumption, we have U2 and HI. So enthalpy through the inlet. This refers to the enthalpy corresponding to pressure and temperature 1 megapascal and 300 degrees centigrade. So if you go to the steam table, 1 megapascal pressure, 300 degrees centigrade temperature, you can find out the enthalpy at state 1. And you can use the same enthalpy as the second property for state 2, where you have pressure given to you. So you can use the pressure and the internal energy at state 2, which is equivalent to the enthalpy entering the system HI. You can use both the properties to find out the final temperature of your system. Clear enough? I'll stop over here.